Hey guys, welcome to part 2 of problem set 3, the atom. Numbers 5 through 9. All right, starting with number 5 here. So this is going to cover your parts A and B that you have in the problem set. Just for time's sake, I combined them into one problem because it's practically the same thing, okay? So naturally occurring bromine consists of two isotopes, the bromine 79 and the bromine 81. Use this information to calculate the average atomic mass of bromine. Okay, so the way that we find the average atomic mass of any substance is by multiplying the masses of each type of isotope by their particular abundances. And in fact, this is how we get the numbers on the periodic table. This is how we get the atomic weight on the periodic table. I'll just put PT here, PT, okay? That's how we get these numbers. We just multiply the abundances of every type of isotope, add them together, and that's the molecular weight or the atomic weight of any particular substance. Okay, so the way we do that is simply by, like we were just saying, we just multiply each mass by the percentage, right? And the reason that they give you this number is because you can't just use 81. In fact, 81 is just it's mostly an approximation. And so we just use this value, 80.9162906. It's more specific, okay? And then we'd say times 0.4931, okay? And notice that we're going to have to use sig figs here. So we're at multiplication and division. Whoops, multiplication and division. And this has 4 sig figs, so our answer will be limited to 4 sig figs here. And then we have to do that same thing with the 79 isotopes. So I'm going to put 78.9183371, okay, times its abundance, which is 0.5069. Remember, with percentages, we have to move the decimal over 2 places in order to do that, okay? This is also limited to 4 sig figs, so and don't get confused. I'm not dividing by 4 here. I'm just saying that this is 4 sig figs. All right. So here you should get actually 39 point. You'll get like 899 something, right? But in order to get 4 sig figs, you'll have to round it up to 0.90. Okay. And then down here we actually get exactly 40. It's a 40.00. And then if you add these, you get the following number, 79.90. And if you look on the periodic table for under bromine, right, bromine, here's bromine 35, right, you will actually see the number 79.90, and in this case they have 4. If we had had more significant figures in these percentages, we'd probably get to up to 4 over there. But this matches bromine. And in fact, any element that you end up doing this for natural abundances, it should always match or at least be really close to the number that you see on the periodic table, okay? All right, so number 6, naturally occurring strontium has 3 stable isotopes, strontium 86, 87, and 88. Remember, these can also be written like this, okay? Each has a different weight, which contradicts the idea that atomic weight is a defining property of an element. Why are all 3 types indeed the same element? Okay, remember back in part, number 2 here, we said that what is an isotope? An isotope are atoms from the same element but with different number of neutrons, right? Okay, so that means that neutron count is not a defining property of an element. And in fact, atomic weight, by definition then, because atomic weight includes number of neutrons, is actually not a defining property of an element. It's actually, this is actually a false idea. They've kind of tricked you here, okay? And so they are indeed the same element. Why? Because of the number of protons is the same, okay? And that is the defining property of an element, is the number of protons. Atomic weight is not a defining property of any particular element. Strontium, in this case, because it has the 3 isotopes, these are all strontium because they all have the same number of protons, but they do have differing numbers of neutrons, okay? All right, letter B here. Chemical analyses conducted by a Mars rover robotic vehicle produced the strontium isotope data below. Does the average atomic mass of strontium in this sample differ from that on Earth? All right, so here we've got this table, and honestly, we're just going to do exactly what we did here. And I'll just put an X here as a times. We're going to multiply here. And just remember, we got to put this as 0958 here, or whoops, not 58, sorry, 86, 086, and then 0.056. These are percentages, right? So that's what we're going to do. And then this would be 0.8258. Whoops, 58. And then just remember that when we're doing these, to keep in mind the significant figures. Usually the percentages are actually going to be your limiting sig figs. So here we've got, actually I'll just write the 3 here. I'm going to put 3 sig figs, 3 sig figs, 3 sig figs, and then 4 sig figs. All right. So when you multiply these together, you should get, let's see, we get 8.47 using correct sig figs here. Here we get 6.57. And then for the last one here, I get 72.59. Okay, so now what are we doing? We're adding these together, right? And up here, when we added these together, these were both specific to the same place, so we were able to get an answer specific to that place there. Here, it's the same thing, actually. They're all specific to this 100ths place. And so my answer, if I add these together, I get 87.63. And I'm limited to being specific to that place. And luckily, I don't have to round up or anything or round down. So we got 87.63. What would this be? AMU, or grams per mole. And how does that compare to the 87.62? Well, it looks like it's just a little heavier. So we would just say it is a little heavier on Mars. All right. Okay, number 7. The following elements all have 2 stable isotopes. Okay, use the average atomic masses of the elements to determine which isotope in each of the following pairs is the more abundant. Okay, remember here. Let's look at strontium. If you look on the periodic table, you get this value, right? 87.62 for strontium. Now, if you were to round this up, right, what that rounds closest to 88. So strontium, I would assume that the 88 isotope, because it's the closest to 88, is going to be the most abundant isotope. And if I look here, yep, sure enough, 82.58. That's the highest abundance, right? Same for bromine. Here I've got the 79 isotope and the 81 isotope. In fact, those are the 2 most abundant. Technically, this rounds to 80, but I know, but they tell me that these are the only 2 stable isotopes. So I would only be able to go down to 79. So same idea here. When you're looking at which isotope is most abundant, just look at the atomic mass or atomic weight shown on the periodic table. So for carbon, I see here that the number down here is 12.001. So that means that means carbon 12 must be the most abundant. It's the one pulling all the averages towards itself. So it must be carbon 12. All right, so that's how we want to look at these. Okay, so hydrogen 1, hydrogen 2. So okay, we have hydrogen 1 or hydrogen 2. Let's see. Whoops, not helium. Hydrogen. So if I look at the mass, it's 0.0794, something like that, right? Grams per mole. And so that's closest to 1. That's closest to 1. And so hydrogen 1 must be the most abundant isotope. And then C here, if I look at fluorine, okay, fluorine, let's say I've got 9 protons, right? And then fluorine, it's got 18.998 grams per mole, and that rounds up to 19. So that must be closest to the fluorine-19 isotope. That must be the more abundant isotope. Okay, so pretty straightforward. Just look at the values here and see which one is closest to the atomic weight. Number 8, pencil lead is actually from a carbon called graphite. If a single carbon atom, we'll just say carbon atom, has a diameter of 1.54 angstroms, or how many carbon atoms could sit side by side, the width of an exclamation point drawn by your pencil. Okay, and then assume that this is how wide your pencil is. Okay, so this is going to be a dimensional analysis because what we're trying to do is take the width of the pencil and somehow turn it into number of carbon atoms, okay? Number of carbon atoms. So that's how you know you're going to do a dimensional analysis, when you're trying to convert one unit of something into some other unit, okay? So I'm going to write a list here of my conversion factors. So I know that 1.54 angstroms is equal to 1 carbon atom. All right, and then I know that there are 10 angstroms in 1 nanometer. And that's about it. And remember that we start every dimensional analysis with the uncertain, or with the measured value that they give us, okay, the measured value. And in this case, this here is the measured value, 0.05, right? That's 0.05 millimeters. That's a measurement. Millimeters is a measurement, and it's not a conversion factor per se. Technically, you can say 0.055 millimeters per, line drawn or whatever, but we don't need to put that. So 0.05 millimeters. And within this 0.05 millimeters, I need to figure out how many carbon atoms are there. So I'm going to go from millimeters, and I see that there's a conversion factors to angstroms. And I know that if I can get to angstroms, I can get to carbon atoms. So I'm going to turn this first to meters. So I know that there's 1,000 millimeters in 1 meter, so that I can get this into nanometers. So I'm going to say 1 nanometer, or 1 meter has 1 times 10 to the 9th nanometers. Okay, and that way these guys cancel, this guy cancels, and now if I were to stop here, I would get an answer that's in nanometers worth of the length of the width of this pencil. But I don't need that, do I? I need to go from nanometers to angstroms. So I got 1 nanometer is equal to 10 angstroms. And then I know that there are 1.54 angstroms for every carbon atom. And the beauty of this type of question and doing this kind of differential analysis is I don't have to go through the mole, right? They didn't give me a mass or anything like that I have to go through Avogadro's number, you know, the 6.022 times 10 to the 23. I could just do all this math here, or do just these conversions of lengths, and I get here in carbon atoms. Okay, and then I just multiply everything on the top and divide it by everything on the bottom. And if you do that with correct sig figs, in this case we only have one sig fig, right, from the 0.05, so we won't really worry about it. But if you do it correctly, you should get, let's see here. You should get about 3.2. 3.2 times 10 to the 5th carbon atoms, okay? Somewhere around that ballpark. So notice that we started with a measured value. We converted into something else. We made a list of all the conversion factors that we needed. And then we just used dimensional analysis to get it into the unit that we needed to. And in this case, it was the carbon atom that we needed. So hope that made sense. And we'll be kind of doing this this dimensional analysis a lot throughout the semester. So I would get really comfortable with doing stuff like this, okay? All right. On to letter B here. In fact, letter B is going to be pretty simple. Letter B, all you have to do is take this same dimensional analysis. In fact, I'm going to erase this here. And just add one more thing, right? One carbon atom. They're asking how many protons are in this line. I know that one carbon atom, based on the periodic table, has 6 protons, right? So all I have to do is multiply the last number I had by 6. And if you do that correctly, using just a couple sig figs, in this case we would have to go, we had about 2 sig figs here. I guess that should have been 1 sig fig here, so we'll just say this was 3.0. 3 or just 3 times 10 to the 5th, and then down here we would say, 3 times 6 would be 18, and I guess we would have to round this up technically. We'll just leave it here, 1.8 times 10, and then this in this case to the 6th protons. All right, so that's how you'll go about that. Typically on a question they'll actually give you a number that's a little more specific with more sig figs, so they won't be quite this general. But that's generally how we do this dimensional analysis here, okay? All right, last one, number 9. A single silver atom has a mass of 107.87. How many silver atoms are in a cube of silver that is 10 millimeters on each side if the density of silver is 10.49 grams per centimeter cubed? And then they give you this conversion factor. Okay, so now, before you use this conversion factor, I actually want to exit out because you technically don't need it, and I'll show you why. It's actually a little more, I think it's a little more complicated if you use atomic mass unit to grams conversions. I think it's just way easier if you just use this value in terms of grams per mole, because you'll actually learn that's how we measure these. This is actually the same as AMU, okay? So first, we need to figure out what is our measured value. Here is our measured value. Now, this is in length, right? This is the length of a side of a cube. So I'm going to say this is equal to 10 millimeters, and that's my measured value. So somehow I have to get from 10 millimeters to number of silver atoms. Number of silver atoms. And I'm going to write this. So this is going to help me somehow, 10.49 grams per centimeter cubed. And then, like I said, trust me, we're not going to use this conversion. There is a way that you can use it, and I think it's a little more complicated. And it's not a way that we'll be using throughout the rest of the semester. This way we will be. So I'll just show you how we do that in a second, okay? All right, so 10 millimeters. Okay, so I notice that there's centimeters cubed here. That's a volume. And I have some sort of length side here. So let's maybe turn this into centimeters. Okay, so how many millimeters in centimeters? Okay, it's 10 millimeters. I know that there's 1,000 millimeters in 1 meter. And that in 1 meter, I have 100 centimeters. Okay. And then I would cancel 1 0 there and then 2 zeros. Okay, so that's just 1 centimeter. 10 millimeters is just 1 centimeter. So remember that the volume of a cube is just all the sides multiplied by itself. So I'll put length cubed. And in this case, 1 centimeter cubed is just 1 cubed centimeters cubed is just going to be 1 centimeter cubed. So this is the volume of the cube. All right, and that actually makes this a lot easier. So I just say this is now my measured value. So 1 centimeter cubed multiplied by 10.49 grams per centimeter cubed. Okay, this would give me the mass of that cube because this is the density of silver. Okay, but I don't need the mass of silver, right? What are they asking for? Silver atoms. So I got to go through this molar mass here. So 107.87 grams for 1 mole of silver. Okay, that would give me moles. Okay, I don't need moles. I do need molecules or atoms. So I'm going to go from 1 mole of Ag of silver to 6.022 times 10 to the 23. You're just going to want to memorize that number. It's just going to be so much more helpful if you can just have it on hand. Atoms of silver. Okay, and that's what they're looking for. So I noticed that all the units that I need cancel, do in fact cancel. So from there, we're just going to multiply everything on the top and divide it by everything on the bottom. And if you do that using sig figs, remember this is 10. 10 only had 1 sig fig, right? There was no decimal here, and so that didn't make it significant. That didn't. There was only 1 sig fig there, so we only had 1 sig fig. That will limit our sig figs to 1. So we get about if you do it right, it'll come out by about 5.86 times 10 to the 22. But we'll just round that up to 1 sig fig, so 6 times 10 to the 22, and then silver atoms. All right. The other way that you can do that using the AMU is a little more complicated in my opinion. You could just have done the same thing, so gone to this grams, and then instead of using grams per mole, you would have gone to 1.66 times 10 to the negative 24 grams, and then that would be per 1 AMU, and then use the AMU 107.87 AMU for every 1 mole of silver, and then from there 1 mole of silver, and so on and so forth. So I just think it's a little easier if you just use the grams per mole, because quite honestly, this is up to this point, this is probably the last time you would use AMU, and in the next problem set you'll be using the mole a lot more often. So grams per mole would be a lot easier to know. All right, so that finishes it for problem set 3. I hope that was helpful.